Good afternoon. So, in the last lecture I was talking about various catalytic reactors, say two phase system and multi-phase system like three phase system. Let us continue the same today also, and different kinds of three phase or two phase reactors which I was discussing last time. If you look at their schematic, these are different kind of two phase reactor where you have a gas or a liquid in the presence of some solid. So, catalytic reactor. So, when you have a just like a gas, liquid or solid, it is a three phase, but when you have a gas, solid or gas, liquid. So, it is a kind of what I told a packed bed, simple packed bed reactor, when you have a gas from the top or bottom and liquid or the catalyst is in the reactor. So, you have lesser number of resistance. So, design becomes little bit simpler, but these can again be a kind of a CSTR like this kind of system, a tank type of reactor. It can be a kind of bubble column reactor, which is very common nowadays, especially when the heat transfer is an issue, and it can be a kind of just a mainly for the gas solid reactions, a packed bed reactor or a fluidized bed reactor. So, you can see here the gas which is passed from the bottom and the product and the unreacted reactant comes from the top, and the catalyst is placed in this bed like this. So, distribution of this is very important, how the catalyst particles are distributed, right, in presence of some inert is mixed to have the heat dissipation. So, regeneration of the catalyst is difficult in this kind of reactor. The another one, as I said, where you have a good contact between the gas and solid. So, reaction is little in terms of back mixing, if you look at it will be more here in the degree of back mixing, because it behaves like a CSTR as I discussed in my last lecture. These are again a kind of CSTR tank type reactor, where when the mixing is the problem or mass transfer is an issue, then we prefer a gas liquid reactors in the form of something like a CSTR. So, you have a well agitated tank reactor here, right. It can be a kind of slurry bubble column reactor also, then it becomes a three phase system. So, right now these are the simple a gas liquid reactions where you have the gas and liquid. So, these can be non catalytic type of reactors also. So, the different type of systems when I was talking yesterday, that heat transfer when the reaction is exothermic or endothermic. So, we put a multi-tubular multi-bed reactors. So, this is a kind of multi-tubular reactor here, if you can see here, and this is a single bed reactor. So, again the type of it can be a heat transfer. So, you can see a jacketed here outside. So, this is just some heat transfer of fluid which is passing through the jacket or agitated, it is not agitated, but it is a jacketed. So, it is a kind of cell and tube type of heat exchanger. So, continuously the cooling can be done here when the heat is generating throughout the system. It can be a multi-bed reactor, which I was talking just for sulfur dioxide oxidation. So, one bed, second bed and third bed, and in between we have the heat exchanger, right. So, this is just a geometrical picture of that what I was discussing yesterday. It can be a shallow bed type reactor, where you have just the layers thin in the form of thin layer, and it may be metals, right, a catalytic net. So, just like in the case of automotive exhaust, you have a small tube and the gas or the exhaust gas pass through these kind of the wire gauge, right, platinum wire gauge or all. So, this can be just a channels here or nets here, and the gas passes through that. And this is again a kind of fluidized bed reactor, and which is again a important kind of gas solid reactor here in the two phase system. Three phase system is more complicated. So, I will just discuss this part today. Here you can see that you have a solid inside the reactor, right, a bed, and then the flow can be co-current or counter current. So, that also it depends on the concentration difference which is required, right, or the kind of the contact between gas, liquid and solid which is desired. So, both type of combinations may be used. So, here you can see the liquid comes from the top. So, we need a distributor here. So, distributor design itself is a complicated job, and one needs to identify a good kind of distributor, right, the number of holes required, right, and diameter of those holes. So, to avoid the maldistribution inside the reactor. So, different kind of distributors are available, and then you need how to place the catalyst, so packing, right, inert may be also kept along with the catalyst. And this is what you can see here. So, you have a gas from one side. So, this is just a kind of co-current operation, right, both liquid and gas comes from the top like this, here the liquid and this is the gas. So, how to get a good contact between gas, liquid and solid, right. So, it can be a low flow rate of the gas, low flow rate of the liquid, or it can be a high flow rate of gas and liquid. So, this is a kind of a downflow trickle bed reactor, and I will talk on that little later. This is again a co-current type of upflow packed bed, because the flow can be downward side or upflow. So, this is a kind of upflow. So, you can have a good contact between gas and solid and liquid compared to this, right. So, because these the channeling flooding problems can be minimized in this kind of case system, right. This is a bubble slurry bubble column. So, one is bubble column reactor when you have a gas liquid, right, with no solid. Here you have a solid which is in the form of basically catalyst, fine powder of the catalyst and kept in the form of slurry. So, already a liquid is here. So, you need a kind of agitator also to make them in suspension, and the gas which pass from the bottom and liquid is also the product which comes, that is taken continuously from here. So, it is a kind of continuous reactor and a bubble column or slurry bubble column reactor. Same thing here, this is a kind of 3-phase fluidized bed reactor. So, you have the solid inside the bed, you have the liquid, right, it can be in the form of suspension, and the gas is being passed from the bottom continuously. So, gas comes out, liquid goes in, liquid comes out along with the product, and that is you have to decide what level or how much liquid product is to be collected accordingly. Just like in the case of Fischer-Tropsch reactions, this slurry bubble column reactors are very common. Same thing in the case of 3-phase fluidized bed reactor, the various heterogeneous catalytic reactions, we have the fluidized bed type of system also, where the hydrogenation reaction, say nickel catalyst is used, right. So, that is the hydrogenation of oils basically is done in these kind of reactors, slurry type of reactors, right. And this is again a type of tank reactor, which is a CSTR type of reactor in the form of slurry. So, the design complications vary depending upon the type of reaction, depending upon the catalyst which is used in the process. So, one need to identify a definite process or upflow, downflow, or a combination of the reactor systems depending upon the process. This is just the details of that what I was talking, a suspension reactor where you have the solid particles are in suspension, suspended form. So, you need a kind of agitator to have a well mixing, right. So, basically the mass transfer problems are minimized by using this kind of reactors, right. So, gas is continuously passed through the sparger. So, a good kind of sparger is required. The size of the catalyst particle becomes very important. The bubble size, liquid in the form of bubble, right, gas bubble. So, these sizes are important. How can you make a good contact between gas, liquid and solid, because all these resistances may be important, and how to enhance the kinetics of the reaction. So, all these factors becomes important when you select the overall rate of the reaction, and accordingly the reactor design is required, or it is important to select a proper type of reactor. This is a kind similar, but this is a continuous type, a plug flow type, that is a combination of CSTR and plug flow. So, suspension reactor which I was discussing, I will just talk on little again on this. So, suspension reactor which is similar to a bubble column reactor, a continuous type of reactor. So, gas is being passed through the sparger, liquid solid is already there and liquid is passed from this, right. So, that is a slurry here, and the particles are kept in suspended form, right. So, again you need to decide what is the particle size, right, what is the type of liquid, and just like in a fluidized bed column, the similar theory of hydrodynamic conditions are also required to be studied. This is very important, especially in the hydrotreatment reactions in refinery or petrochemical industry or advanced air oxidation process, the trickle bed reactors are used, right. So, here again you have a gas and liquid coming from top, and then it is coming down from the bottom. So, gas hold up, liquid hold up, then contact between the gas solid, wetting, wettability. So, there are many factors involved in which decides the or decide the efficiency of the process, right. So, we need a good kind of contact between gas, liquid and solid. We need a definite kind of wettability, because wetting and wettability both are very important in these kind of multi-phase reactor, right. So, dead zones which may come because of the inefficient type of catalyst or inefficient wetting during the reaction. So, there can be the different kind of say pressure, depending upon pressure, depending upon the flow rate of gas and liquid, the flow or hydrodynamics may be affected, and because of that the pressure drop may be an issue, energy consumption. So, how to minimize the pressure drop and drag force between the gas and solid or liquid gas, liquid solid. So, interfacial tension becomes important. So, there are many factors which where interfacial science and engineering is also involved, right. Reaction engineering is involved, hydrodynamics, fluid mechanics is involved. So, a combination of all these need to be studied in order to design these kind of reactors. So, compared to packed bed reactor, a design of multi-phase reactor becomes or three-phase system becomes much more complicated. But if you look at the comparison, right, a catalytic fixed bed reactor just and a multi-phase reactor. So, catalytic fixed bed reactor it has some advantage and but disadvantage also. So, each kind of reactor system will have some advantage and some disadvantage also. So, one need to one has to do all these exercise in order to finalize a best reactor for the given process in the presence of the catalyst. So, here the catalytic fixed bed reactor, the fluid flow regime approaches to the plug flow, because most of the time I say that the dispersion is to be minimized, right. So, axial radial dispersion which contributes a kind of non ideal flow, right. So, that is to be avoided, and when you have a kind of fixed bed reactor, one can select the proper design condition in terms of the height of the reactor, diameter of the reactor, size of the catalyst particle, and can approach to a plug flow condition, right. So, you get when you have a plug flow condition, I told you that the because the conversion down the length of the reactor will be higher if you do not have any kind of non ideality in the reactor, right. So, this is one advantage here, you get high conversion. Pressure drop is low because it is a fixed bed reactor, one can decide the particle size. So, depending upon the particle size, the pressure drop can be minimized or reduced, and since the hold up is high, owing to the high hold up, there is a better radial mixing and channeling is not encountered. So, this is what I was talking in the case of a fixed bed reactor, or when you compare a two phase, right. So, when you the liquid flow, right. So, what happens, the liquid bypass the catalyst, it just comes from the side of the wall, right, or it comes from the void space between the particle. So, here you can have a better design, right, and flow conditions are different. So, one can look at the hydrodynamics and look at the hydrodynamics to evaluate the RTD and try to find out the condition when the reactor resembles like a plug flow reactor. So, that becomes very important in the terms of the design of reactor or selecting a best kind of reactor and working under ideal conditions or making it ideal for the conversion. So, this is what that channeling is avoided or minimized in the case of the fixed bed reactor, and catalyst loading is high per unit volume of the reactor volume. So, that is again important, because when you calculate the overall productivity, that depends on the mass of the catalyst in the reactor, right. So, per unit volume, if you look at, you can have high mass of the catalyst in this case compared to CSTR, as I said that the mass of the catalyst requirement will be low for the same conversion. So, this is the advantage of the fixed bed reactor, but disadvantage wise, I told intraparticle diffusion resistance is very high, because you have to select a definite particle size, right. You cannot take very fine powder, because pressure drop will be very high, right. So, that is an important aspect. Again, when you look at a reactor design, you have to look at the hydrodynamics and dP by dz, pressure drop, right, per unit length of the reactor, and that is to be minimized, right. So, that is one thing, that if you take the larger particle size, your pressure drop will be low, but the problem will be intraparticle diffusion resistance, because effectiveness factor, which I discussed in my last lecture, that depends on the particle size also. So, intraparticle diffusion resistance is one of the issue which will decrease the overall rate of reaction. Just like if you have a ammonia reformer or ammonia the production, right, where you have a reformer and if the catalyst effectiveness factor is very low 0.001. So, it means the rate of reaction will be very low. So, that is why a new kind of reactor design is required, where you look at a monolith type of reactor, which are the kind of channel type of reactor, right. So, micro reformer concepts, that is what used or being used to have higher conversion or higher rate, where the diffusion resistance is an issue, right, especially when you have when microporous catalyst or non-porous type of material. So, then these resistances becomes more and more dominating, right. So, that is one issue. Second thing is the heat and mass transfer, because heat removal or concentration gradient, right, that may generate in the case of the packed bed reactor, right, because you do not have any kind of stirrer there, right. So, there will always be a kind of concentration gradient from bulk to the center of the catalyst, right, and down the length as well as radially also there will be this kind of concentration gradient, right. So, heat removal is an issue in the case of the fixed bed reactor, and same thing catalyst replacement is difficult. So, that is why I told the fixed bed reactor should be recommended when the deactivation of catalyst is very low, right, or catalyst life is high, something like say a minimum of 1 year, right, 1 to 3 years, just like in the case of hydrodesulfurization reaction, or in the case of your ammonia production, the life of the fertilizer industry, the life of the catalyst roughly 3 years. So, there these kind of reactor can be used, provided the other problems are solved, right. So, that is one disadvantage of the fixed bed reactor. Same thing in the case of fluidized bed reactor, because when the deactivation is an issue, we prefer a fluidized bed reactor, right. So, it has again some advantage, but simultaneously some disadvantage, right. So, one thing is that smooth liquid like flow, right, because it is a fluidized bed. So, you just the particles are flowing in the just like a fluid, right. So, only thing that you need to have some high flow rate or superficial gas velocity, all these hydrodynamic studies need to be done in order to make the bed or particles fluidized at all the time, right. So, this allows a continuous controlled operation with ease of handling. So, particles can be removed from the system, right, and they are well in contact with the reactant. So, your rate transfer or heat transfer, mass transfer, these problems can be solved to some extent. So, near isothermal conditions can be obtained due to rapid mixing of solids. So, this is another advantage here, that the isothermal conditions can be maintained. Intraparticle resistance is low, because the particles are now smaller here, right, of the order of 100 micron, 200 micron. So, the intraparticle resistances are lower, right, and that will be again an advantage in terms of heat and mass transfer rate, because surface area per unit volume of the catalyst is very high, because the particles are now smaller. So, heat transfer and mass transfer problems are solved to some extent, right, but again there are some disadvantage. So, first the particles are moving up and down, right. So, there is upward and down flow, right, up and down. So, that is one violent particle motion, right, of particle, and it tends to homogenize all intensive properties of the bed, right. So, that is what I just like a CSTR I said, complete back mixing, there is a degree of max mixing, right. So, because of this, thus it is not generally possible to provide an axial temperature gradient, which might be highly desirable in some instances. So, in some cases where you need some kind of temperature gradient, right, then it is difficult, because although this is not a very big issue, not in all cases the temperature gradient is desired, right. In most of the cases the gradient is not desired. So, in that, so this is one problem, but because of the well mix, just like in a CSTR you cannot get the gradient of temperature. So, in this case also the temperature gradient is not generated. Second, erosion by abrasion of particle is serious issue. So, this is what the loss or attrition of the particle, because they are moving like this, right. There is a kind of attrition between the particles, and the particles, if they are soft, right, if they are not stable mechanically, then they will crumble during the reaction, and then they will leave the reactor bed. So, there will always be a loss of catalyst during the operation. So, that is an important issue. So, how to make the catalyst stable, that is important here, right. So, this is the second and third is again the particle attrition. So, these are some issues which are associated with the fluidized bed reactor. I was just talking about trickle bed reactor. So, trickle bed reactor again, as I said, the hydrodynamics is very important, and to decide the gas flow, liquid flow rate or superficial gas velocity, and then the hold up gas liquid. But these trickle bed reactors are a type of multi-phase reactor and widely used in the process industry, right. So, especially when the mass transfer or the solubility is an issue, the hydrogen say is difficult to dissolve in the kerosene. So, these kind of reaction you need a kind of pressure, right, high pressure is required to make it soluble, right. And then when the and depending upon the concentration, depending upon the solubility and the solid type of solid which is your catalyst. So, you will have a kind of gradient, right, concentration gradient, temperature gradient, and if this gradient exists, then there will be mass transfer resistance, right, heat transfer resistance. So, these are some issues which need to be addressed when you look at a trickle bed type of reactor. So, let us talk about trickle bed reactor, because this is one of the important reactor used in the refinery and petrochemical industry, and also for the advanced oxidation or wastewater treatment. So, trickle bed reactor is one of the common type of 3-phase reactor, right, and here the gas and liquid they flow co-currently downward over a fixed bed of catalyst particles. So, most of the time it is from upper side to lower side, right, downward flow, but nowadays counter current trickle bed reactors are also being practiced or tested or at R&D level, right. So, to have the more and more concentration difference. So, co-current downflow of the gas and liquid over a fixed bed of catalyst, this is what trickle bed reactor, and liquid trickles down while gas phase is continuous, right. So, what does it mean? Generally the liquid flow rate is low, right, relatively lower liquid flow rate, although the gas and liquid both flow rates are low, but still at a low flow rate what will happen? Suppose you have a solid catalyst particle like this, which is porous material. So, it means it is saturated with some liquid. So, when the liquid comes, so it at a low flow rate what will happen? It will come like this, it will trickle over the surface of the solid like this. So, this comes like in the form of rivulets or droplets, and then it comes like this, right. So, there is a thin film of the liquid on the surface of the solid, and this liquid is already saturated by the liquid, right. This liquid is already there in the pore of this catalyst, and now when you have a gas, so gas will be somewhere here, right, and this gas is diffusing through this liquid film, which is a bulk of liquid and surrounded by again a liquid surrounded by a solid. So, I will talk on that. So, here will be a kind of resistance this, right. So, there will be a constant, the gas has to penetrate this liquid film and then come to the surface of the solid and then diffuse inside for that reaction, right. So, active metal is there or catalytic active sites are inside, what we have discussed earlier in the gas solid reaction also. So, the on the surface of the solid, the reactant where the liquid is already present in the pore, the gas reaches there and then it reacts. So, if I write a reaction something like this, so it is a gas A reacts with some liquid which is B, right, in the presence of a solid which is a catalyst, and then it transforms it to some product P, right, which may be a gas or liquid, right, and whatever that, and that product P comes out of the pore. So, this is what we have to look at, that what are the resistances offered, because it is a mass transfer dominating, because the solubility of the gas is important here. This is something like kerosene hydrogenation, right, or removal of sulfur from the kerosene, right, diesel hydrodesulfurization, right. So, we need to look at that where the solubility of hydrogen in diesel, right, and then the transfer of this hydrogen gas from the diesel liquid which is there, and through that to the surface of the solid, and then come to the pore of a catalyst where already some diesel is present, right, and then these two react like this, and the sulfur which I am talking here. So, when I say that gas is your hydrogen, when I say this B liquid, so it is some sulfur compound, right, benzothiophene, dibenzothiophene or mercaptan, and then it converts it into a sulfur compound, right, or hydrogen sulfide basically. So, that comes out of the pore, so which is a gas basically. So, this is what we look here. So, generally in trickle bed reactor, the various flow regimes, they will be here what I discussed, right, depending upon gas, liquid flow rates, right, fluid property and packing characteristic. So, it means the viscosity of liquid is very important, right, gas properties are important, Reynolds number will be important, right. So, we have to just identify some dimensionless numbers, or we have to correlate the flow property, pressure drop in the reactor, right, and how to get a good contact between gas and solid. So, that will depend on mass transfer coefficient of the gas to liquid, mass transfer coefficient liquid to gas in the liquid film, and then from liquid to surface of the solid, then catalytic reaction kinetics. So, all these factors need to be incorporated in this. So, pressure will be important, pressure will enhance the solubility, simultaneously temperature will be required, right. So, one needs to look at all these. So, let us talk more about on this trickle bed reactor. So, in this trickle bed reactor, the gas and liquid mixture leaving from the bottom of the reactor is separated. This is just like a packed bed reactor, otherwise it is similar to a packed bed reactor. The only thing that your liquid flow rate is very low. So, the liquid just trickles on the surface of the solid, right, just like in a solid surface, and on a ball you put some water in a thin film. So, water will spread like this, right. So, that is here what the right, and that whatever the product you get separate and then recycle the unreacted one. So, advantage of this type of reactor is that they have good residence time behavior, right, of the liquid and gas stream, and the possibility of operating even at high liquid flow rate, right. So, it can behave like a plug flow also, that is what I was talking, that you have to just maintain the condition, and then under what condition it resembles, that is RTD study can be done, right, or flow rate of gas, flow rate of liquid on different shape and size. So, here it is basically a mass transfer control reaction, as I said. So, most of the time this Kg or Kl may be important, that is mass transfer coefficient of the gas phase, mass transfer coefficient of in the liquid phase, these may be important, right. So, one has to look at how these mass transfer coefficients can be enhanced, right, in order to minimize the resistance. So, we will talk on that. Back mixing is not an issue, because it works like a fixed bed reactor, right. So, that height is very large. So, I told that to avoid the back mixing, generally the L by D ratio should be kept large. So, high length of the reactor is desired. So, superficial velocity is again important in the case of trickle bed reactor, because the depending upon the liquid to gas or L by G ratio we call here in the case of trickle bed reactor. So, this factor becomes important. What is the liquid flow rate, what is the gas flow rate. So, this L by G ratio, right, gas, liquid to gas. So, depending upon that you will have the pressure drop variation, and also when the pressure drop change, then you have the several other secondary problems inside the bed. So, you need to look at all those. So, here in this case the liquid flow rate is roughly 10 to 30 meter cube per meter square per hour, right, which is what you call the mass velocity, right. They or one can define in terms of the superficial gas velocity also, right. So, superficial gas velocity of gas. So, U g divided by U L superficial gas velocity of the liquid, which is based on the tower diameter, right. So, 10 to 30 meter cube per meter square per hour is the flow rate, right, of the liquid, and flow rate of the gas is again 300 to 1000 meter cube per meter square per hour, the typical range of the data for the trickle bed, right. Solid liquid separation is not required, right, because they are already in the bed, right. So, separation of solid and liquid is not required in the case of trickle bed reactor. So, this is another advantage here. Disadvantage is that heat removal, because it is a packed bed reactor, right, basically it is a packed bed reactor. So, heat removal is an issue. So, if the reaction is exothermic, then just like so one needs to look at how to control the temperature, right, and occurrence of hot spot within the potential instability. So, when the heat removal is an issue, and if reaction is exothermic, then the problem is something like hot spot formation, right, where the temperature at a localized point may be very high, right, high temperature at particular point, and that will damage the activity of the catalyst because of recrystallization, what I said, sintering phenomena. So, this is an issue in the case of trickle bed reactor, because reaction hydrodesulfurization, hydrocracking, these are highly exothermic reactions, right. However, since the reactors are generally operated adiabatically, so this is desired here, right. The relatively poor heat removal is not a necessarily problem. So, one needs to look at these conditions for operation, how much heat generates during the reaction, or how that heat can be removed as soon as it generates during the operation. So, that is important, especially when the reaction is highly exothermic. Stream formation in large diameter reactors and wall channeling in small diameter reactors can lower the reactor performance. So, this is what I told you, the selection of the proper height, that is length of the reactor, and the diameter of the reactor is an important aspect when you look at these. So, we need to look at what is the height of the reactor, which we call length of the reactor, what it should be the diameter of the reactor. So, basically it is L by D, that is one thing. Second thing is what catalyst diameter should be selected, right. So, that is again important. So, basically the wall flow, you have to select a D by D ratio, that is the diameter of reactor to diameter of the catalyst particle as high as possible. So, roughly more than 20 if you keep, or then your wall flow are neglected. So, wall flow means what I said, the fluid has a tendency, when you have particles here like this and you have a maldistribution. So, what will happen, because of this maldistribution, your liquid will have a tendency to move towards wall. So, it will not go through the solid particles in between. So, more and more liquid will distribute towards the wall. So, a good kind of distributor is very important, right. And again this diameter of the particle and reactor diameter becomes important. So, I told that it should be kept higher, right. And same thing, because you know the plug flow conditions, if you want, then you need to have a L by D ratio, right, a larger L by D ratio. So, more than 30, more than 40, more than 50, right. So, that kind of L by D ratio is desired. So, this needs to be controlled. So, again the issue with this trickle bed reactor or these kind of trickle bed reactor is the hydrophobicity and hydrophilicity, because the suppose you have a solid material like alumina, right. So, alumina catalyst, they if you put water onto that, so it will immediately take that water, right. So, these are known as hydrophilic type material when they wet the surface. So, that surface will be completely wetted, but suppose you have a this same alumina, if you coat it with some plastic material like Teflon, right. So, what will happen, now this polymer, this is a polymer kind of material, and this polymer material will not accept the water, right. So, this becomes a hydrophobic substance. So, now the depending upon the hydrophobicity or hydrophilicity, there will be a kind of wetting phenomena. So, wetting practically you cannot mathematically identify, but it is a kind that what fraction of the surface of the solid is being wetted by the liquid, right, and that decides the efficiency of the process, right. So, sometimes 100% wetting may not be good, right, and a complete hydrophobic substance is also not good, right. So, you need a balance of that in terms of to control the mass transfer resistances at the surface of the solid, right, because liquid and gas has to contact properly in the presence of solid for the transformation of these reactants into a product. So, that is again important, that how wetting should be correlated, right, wetting, wettability, right, and then accordingly the pressure drop will also be affected because of this wetting and wettability, right, viscosity and phenomena. So, that will affect here. So, everything is related here. So, lot of R&D is still being done or required in order to study for the catalyst in a trickle bed reactor for different hydrocracking reaction, hydrotreatment reaction, right. So, this is one important issue. Trickle bed reactors generally, as I said, they are widely used in the petrochemical industry, right, hydrogenation process and production of the basic products, fine chemicals also they are now being tested, right. So, or as I said, advanced oxidation process, say treatment of wastewater, phenol oxidation or removal of oxidation of the organic compounds, right, are being practiced in these kind of trickle bed reactor. And just briefly before going in detail of trickle bed reactor, I will just talk on suspension reactor also, right. So, suspension reactor, it is a kind of again slurry type reactor, where the solid and liquid are together and some stirring is done to have a good contact between the liquid and solid. So, where the again it depends on the where the diffusion is the problem, mass transfer is the problem, then these may be better type of reactor, right. So, in suspension reactor, the gas and catalyst particles are distributed in a relatively large volume of liquid. So, that is just differentiation between the trickle bed and a slurry or suspension reactor, right. Your volume of liquid is relatively large, right here. So, liquid and solid are well mixed in the form of slurry, right. Catalyst concentration, if you look at here, typically less than 3% and particle size is less than 0.2 millimeter. The typical size, there can be a variation up to 0.2 to 0.5 millimeter particle size are used, and same thing here, the concentration can be on a higher side also. In general, the reactants liquid and gas are introduced into a lower part of the reactor together with the catalyst, which is suspended in the liquid. So, generally gas is bubbled from the bottom, just like in a slurry bubble column reactor. So, here the advantage is that you have a good contact between the gas, liquid and solid. So, your transport resistances can be minimized by using the stirrer, right. So, you can have the mass transfer resistances at its lowest level, because you have a stirrer here or a kind of agitation of back mixing there, right. There is another type of reactor in this which I have not shown here, a bus loop type reactor, which is generally you have a jet, right, and from where the gas and liquid are infused or transport, right. So, and it can be external or internal mixing also, recirculating also, right. So, different combinations of these kind of suspension reactors are possible. So, if you look at here in the upper part of the reactor, the unconsumed gas is separated. So, which is here, right, or removed together with the liquid product. So, part of the liquid can be removed and this suspended solid catalyst. So, gas is separated and this is again a kind of here the baffles, and that gives a kind of recirculation within the system. So, you remove the product here, you remove the gas here, right, and this is what the gas and liquid which is continuously recycled in the system. Some advantage, if you look at here in this system, the liquid is in continuous phase, right, in which the gas is dispersed as bubble, right. So, gas bubbles are coming from the bottom and liquid is already present along with the solid. So, liquid is in continuous phase and gas is being dispersed in the form of bubble, right. So, you will have small gas size particles, right, gas bubbles, right. So, now you need to design a sparger, better sparger, so that the bubble size should be controlled, right, otherwise the mass transfer resistance will be an issue, right. So, that is one thing here, and the solubility of the gas, that is another issue, that whether gas is highly soluble or sparingly soluble. So, small bubbles when they so it will be easier to dissolve in the liquid. So, gas has to dissolve and then it will be transported into liquid. So, some Henry law which is related to pressure and concentration in the liquid, gas liquid, right. So, one can use that. So, suspension reactor, they behave largely as a gas liquid system, right. So, along with the solid, and little energy required for suspension because catalyst concentration is low, right. So, the energy requirement for suspension is low, but they behave like a CSTR as I said. So, conversion will be poor or productivity will be low in this kind of reactor. The suspension reactors can be regarded as isothermal with the behavior that approximates that of ideal CSTR tank, that is a steel tank reactor what I said. So, this is what I will just the gas and liquid, they can be recycled during the system, which I said in the case of this reactor here, you can have a possibility of recycling this gas and liquid in the system, right. So, external or internal recycle, both kind of possibilities are there, and same thing in a bus loop reactor where you have a jet and through that you can pass the liquid and gas. So, the reactors are followed by a phase separation. So, you need to separate the gas and liquid, right, in which the liquid is separated from the catalyst and the gas and then recycled back into the system. The advantage, if you look at what I discussed, is that the particles are smaller in size, right. So, diffusion process within the catalyst will not play any role, because you have the Thiele modulus which is based on the particle size, right. So, the effectiveness factor in this case will approach to 1, right. So, that is one advantage, that the diffusion issues are minimized. So, you will have the complete rate or highest rate in this kind of reactor, right. So, this is one, and the complete catalyst is being used here, because it is a fine low concentration of the catalyst and in a large volume of the liquid. So, well dispersed fine powder or particles of the catalyst, they are well dispersed in the liquid. So, the gas will have enough time to contact with these catalyst particles. So, that is another advantage compared to a packed bed reactor, where the most of the particle surface of the catalyst may not be utilized properly, right. So, this is one advantage here, right, and catalyst is completely wetted. So, when you need a complete wetting surface, so smaller the particles and they are in contact with the liquid. So, catalyst has enough time to contact with the liquid. So, all the time they are completely wetted, right, they are not partially wetted. So, efficiency will be higher. So, this is, and the important one what I already said, that because of smaller particles, the diffusion within the catalyst play no role, and if this is the case, then it will have good temperature control and local overheating can be avoided, right, because it is a stirrer you have. So, you have well mixed reactor. So, temperature gradient will not be an issue. So, this type of reactors can be used when there is a deactivation, right, rapid deactivation of the catalyst, because catalyst replacement is possible. So, you have a small concentration of the catalyst and continuously it is coming up, and you separate the gas, solid and the liquid and from the product and then recycle it back. So, if you have a catalyst in the system, you separate it, if it is deactivating, regenerate it and recycle back into the system, or change the catalyst if it is poisoned. So, this possibility, or this is the advantage in the case of a suspension reactor, but again there are some disadvantage, because this is what the separation of the catalyst, you have fine powder, smaller particle size. So, separation of the catalyst and the risk of fractionation and sedimentation of the catalyst in the reactor. If the stirrer is not well designed, or if the density of the catalyst is high, then there may be chance that some of the catalyst will get sedimented, right, or some of the catalyst may, if it is very fine, it may get out along with the liquid, right. So, all these problems, the separation may be an issue. So, this is some problem, this is one problem basically in the case of suspension reactor, but that can be avoided by selecting a proper system, right, for separation of liquid, solid and from the gas. Residence time behavior is again like a CSTR, because I told that all these reactor, bubble column reactor, suspension reactor, slurry bubble column, they are resembling towards a tank reactor, right, steel tank reactor. So, the conversion will be low. So, if the conversion is low and you want the high productivity, right, you need a larger size of the reactor. So, large size of the reactor will be required compared to a fixed bed reactor, which works like a plug flow. So, these are some advantage of a trickle bed reactor. So, which I would like to explain here, because that is very important when these are widely used reactors in the process industry. So, the gas and liquid flow regime, it approach like a plug flow. So, if you properly control the gas flow rate, liquid flow rate, right, and the type of the catalyst, size of the catalyst particle shape, then one can approach to a plug flow. And when you approach a plug flow, degree of back mixing is minimized, right, no axial dispersion, no radial dispersion. So, definitely the conversion will be high. So, that is the advantage, that high conversion can be achieved in the case of trickle bed reactor if properly designed. So, a well hydrodynamic study need to be done, and properly the conditions are to be optimized, and then one can achieve a plug flow design conditions in a trickle bed reactor. So, distributor design is again important in order to achieve the high conversion, to avoid the maldistribution. Then large catalyst particles can be used in the trickle bed reactor, right. So, pressure drop will be low and simultaneously the suppression of the catalyst is easy. Hold up, I will talk that little. So, liquid hold up, that is the volume or amount of liquid which is available, right, in the reactor. It may be dynamic or static, we will talk on that. So, that is low in the case of trickle bed reactor, because trickle bed reactor generally when you have high flow rate, hold up will be high, when you have low flow rate, hold up will be low. So, here in the trickle bed generally it operates at a low flow rate, as I said, it trickles on the surface, right. So, low liquid hold up, and therefore, liquid is homogeneous reactions are minimized, right. So, that is one advantage, because the liquid it is not large volume. So, secondary reaction which may be possible that can be avoided in this case, right. And so, no liquid homogeneous reaction between the liquid phase itself, right. Then pressure drop is low, as I said. Flooding problems are avoided if the distributor is properly designed, right. Proper size of particles have been taken, all these d by d, L by d ratios have been adjusted, and the high catalyst load per unit reactor volume is generally used in this case. So, catalyst mass per unit volume of reactor is high in this case, right. So, that depends on the size and diameter of the reactor, right. So, one can have that advantage. Per unit volume of the reactor, if you take calculate, then the mass of the catalyst is high compared to your suspension reactor, right. Disadvantage again if not properly designed. So, poor distribution, this is a big issue in the case of trickle bed reactor, that is maldistribution of liquid, right. So, that is one. Then partial wetting of the catalyst, right. So, because of the solubility of the gas, liquid, and then it is a surface of the solid. So, pressure conditions, so depending upon the pressure, so there may be that some of the surface of the catalyst may not be properly utilized, that is the liquid is not in contact with that surface, right. So, that is one problem here in the case of trickle bed reactor. High intraparticle resistance, these are the diffusion resistances, right. So, liquid is diffusing into the pore, and then depending upon the resistance, that is the I will just talk on that, but basically it is a kind of effectiveness factor which is right in the into the pore of the catalyst, right. So, liquid is already there and gas is diffusing through that. So, there will be a kind of concentration gradient, right. So, rate will be slowed down because of this resistance. Then radial mixing is right, that is again an issue here in the case of trickle bed reactor. So, there will be a poor radial mixing. So, there will be concentration gradient more and more in the case of trickle bed reactor. Temperature control, you do not have any kind of controlling device inside the reactor. So, and the particles are kept in a larger size. So, there will be a kind of temperature gradient within the pellet itself, in a catalyst pellet if the reaction is highly exothermic. So, temperature reaction is inside the catalyst pellet. So, temperature may be higher, outside it is low. So, there will be a kind of temperature gradient, thermal gradient or thermal stress may generate it right here. So, that is again an issue, and low gas liquid interaction decrease the mass transfer coefficient, right. So, interaction between gas and liquid will depend on the several other factors, solubility, process condition, and but this is again a problem that the interaction between gas and liquid is low. So, because of that the mass transfer coefficient may be low, because it depends on the velocity, superficial gas velocity and other factors, right. So, we will talk on that later. Bubble fixed bed reactor, just I thought that here also we should look at that compared to bubble, what is a bubble fixed bed reactor and then what are their advantage, right. So, it is a fixed bed reactor basically, but we discussed earlier, right, and gas is being bubbled, right, or liquid is being bubbled. So, it is basically high liquid hold up here compared to your the earlier case in the trickle bed reactor. So, basically it is a packed bed, right, and therefore, catalysts are completely wetted, better temperature control and no channeling problem, right. You have a gas is being bubbled and liquid is already there, slurry, it is a kind of slurry bubble column reactor, right. So, but instead of bubbling the you have a fixed bed type. So, you have a liquid, solid and gas may be bubbled from that, right. So, gas liquid mass transfer is higher compared to a trickle bed reactor, because there the flow rate was low, right, liquid flow rate, here liquid flow rate is high, right. And so, in trickle bed due to higher gas liquid interaction. So, interaction between gas and liquid in this kind of reactor will be high. Again disadvantage in this is that axial back mixing is higher than trickle bed reactor, right. So, it is behaving like a CSTR here. So, back mixing will be an issue. So, because of the back mixing, because as I said the conversion will be lower, right. Feasibility of liquid right side homogeneous reaction. So, the mass of the liquid or volume of liquid in the bed is now higher, right. So, there may be a chance of homogeneous reaction between the liquid, right. So, that is again a problem, liquid side homogeneous reaction. Pressure drop is high, right, particles are smaller now. Flooding problems may occur because it is not a well designed, right. So, here you need to minimize these problems, but compared to trickle bed reactor the flooding problems may be severe here in this case. Then again a slurry 3 phase fluidized bed reactor, right. So, here again we have some advantage and disadvantage. So, just I have tabulated them. So, slurry 3 phase fluidized bed reactor, ease of heat recovery and temperature control, because you have in the slurry phase, right. So, particles are fine. So, as in the fluidized bed reactor, you know, whatever the advantage, these will be here also. So, ease of recovery and heat and temperature control is one. Ease of catalyst supply and regeneration is possible. Intra-particle resistance will be low because particles are smaller here. High external mass transfer rate, gas, liquid and solid. So, mass transfer rate is high because the superficial gas velocity is higher in the case of fluidized bed reactor. So, mass transfer coefficient depends on the particle size. So, particle size smaller here, velocity of the superficial velocity is high. So, coefficient will be higher, right. So, that is, but again here the disadvantage, the axial mixing is very high, right. Catalyst suppression may be, right, it may be a problem here because it is a slurry reactor, particles are finer, right, you are fluidizing it. So, the suppression may be, filtration is required from the fine suppression of the catalyst particles, right, from the liquid. High liquid to solid ratio may promote liquid side reaction. So, here liquid volume is high, right. So, liquid to solid ratio is high. So, it means there may be kind of homogeneous reaction, side reactions, right, because the volume of liquid is high, secondary reaction which may happen in the presence of high volume of liquid. And catalyst loading is low if you look at per unit volume, because, right. So, that is again an issue here. This is just an exercise, I have left it for you. You have to name some industrial process based on literature review or, right, references, and then identify the reactions or the, right, which can be carried out in this single bed reactor, in a tubular reactor, multi bed reactor, shallow bed reactor, fluidized bed. So, the same what I have discussed yesterday. Now, you have to just cite some industrial process where these kind of reactors are generally used. Just you have to just find it from literature or exercise it. There is again a problem that compare the trickle and bed and the suspension reactor depending upon the criteria, right. So, means you are whether you will go with a trickle bed reactor or a suspension reactor. So, just have some study on this and what you have understood so far. So, depending upon that for temperature distribution, selectivity terms, residence time distribution, behavior of the liquid, catalyst particle diameter, effectiveness factor, performance. So, you have to look at or compare these two reactors based on these parameters. So, identify which will be higher, in which case what should we do or how to go with these, right, type of, say, to improve the selectivity, whether this or this, temperature distribution, residence time distribution, behavior of liquid, which. So, in each reactor, in each case you have to just talk on that. So, just in continuation of this advantage disadvantage, if you just compare the two 3 phase reactor or multi phase reactor system. So, trickle bed and bubble fixed bed, which I was already I had discussed the advantage, but just very quickly I will go through that. The pressure drop, which is the important parameter which we study during hydrodynamics or when we just compare the two catalysts. So, pressure drop is 1, right. Then heat control, radial degree of mixing, radial mixing, liquid to solid ratio, catalyst wetting and conversion. So, all these aspects I have already discussed, but very quickly I will go. Then in trickle bed reactor, the pressure drop, right, characteristic. So, channeling at low liquid flow rate it comes, right. So, at then the flow rate of liquid is low. So, there will be chance of channeling, right. And in the case of bubble fixed bed reactor, no liquid flow maldistribution, right. So, this is again in the case of bubble flow the maldistribution avoided. So, characteristic in all case the pressure drop, right, heat control, radial mixing. So, all these aspects need to be looked into. Heat control, if you look at in the case of trickle bed reactor, I told that there are no stirrer, right, and particles are larger in size. So, if the reaction is exothermic, then control of heat becomes difficult. So, heat control is relatively difficult in this case, but here in this case of bubble fixed bed reactor, the control, because you have a bubbling gas being bubbled, right, and a kind of stirrer, right. So, can be used or you can control the temperature. So, this is easy here, right, particles are relatively smaller in size. Radial mixing, in the case of trickle bed reactor, radial mixing is poor, right, poor radial mixing, but here you have a bubbles going up, right, smaller bubbles. So, good mixing is obtained, right, it is behaving like a back mix reactor. Liquid to solid ratio in trickle bed reactor, as I discussed, low, here it is high. Catalyst wetting, it is partial wetting is possible, right, here it is complete wetting possible in the case of bubble fixed bed reactor. Conversion in the it behaves like a plug flow, so high conversion is achieved, but here the conversion is poor because degree of back mixing is higher. Same thing the suspended reactor, if you look at different type of reactors which we talked, right, CSTR slurry, bubble slurry, 3-phase fluidized bed reactor, all these we have discussed. So, here the attrition of catalyst may be an issue in the case of slurry reactor, because you have a stirrer there. So, particles may crumble. So, here the particles may crumble. So, if the catalyst is soft material, then you should not use a CSTR type of reactor, right. In bubble slurry it does not matter, right, particles are smaller and they are in the suspension form. So, it does not matter, insignificant. Same thing in the 3-phase fluidized, there is no attrition of the particle, right, catalyst attrition is insignificant. In the case of the mass and heat transfer efficiency, the CSTR slurry has high efficiency, highest efficiency, bubble slurry has high and 3-phase fluidizer is reasonably good. So, both are similar in one way, but CSTR has high mass and heat transfer efficiency because you have used an agitator there, right. Mechanical design is difficult in the case of CSTR, but in the case of bubble, slurry and 3-phase fluidized it is simple, the mechanical, because no agitation, no moving parts are required. So, this is an advantage here in one way, right. Catalyst suppression is easy in CSTR, bubble slurry also it is easy, but in fluidized bed it is much more easy, right. So, one can take it out and separate. Power consumption is highest in the case of CSTR because you need a agitation. Here in the bubble it is intermediate, you need some sparger and bubble the gas is, right, and in 3-phase fluidized it is lowest, right. Same thing for catalyst distribution is uniform in the case of slurry reactor, but it is bubble slurry and 3-phase fluidized it may not be uniform, right. So, I stop here and I will continue again this chapter in the next lecture, right. The same module will be continued in next lecture. So, thank you for today.